SALMON is open source software that performs first principles calculations on the interaction between light and matter. In this video, we determine the ground state of an acetylene molecule as the first example of a calculation using SALMON. This exercise is explained according to the manual on the SALMON website. You can access the SALMON website using this URL https://salmon-tddft.jp. For this exercise, it is assumed that you have completed the installation of SALMON. If you have not done so, please install SALMON. Please refer to Introduction to SALMON Installation in the Documents page of the SALMON website for instructions of installing SALMON. Let us begin the exercise. Click the Use SALMON button on the left sidebar on the SALMON website to display the SALMON manual. Click the Exercise button on the left sidebar of the SALMON manual. Several exercises have been prepared for you to learn to use SALMON. The files necessary for these exercises would also be installed when you install SALMON. On the left sidebar of the SALMON manual, click the C2H2 Isolated Molecules button that is below the Exercise button. In the first exercise, we consider the acetylene C2H2 molecule as an example of an isolated system. An acetylene molecule contains 2 carbon atoms and 2 hydrogen atoms arranged in a straight line as shown in the figure. In exercise 1, we calculate its ground state. To investigate the optical response of this molecule, we need the ground state solution as the initial state. Therefore, calculations using SALMON must first determine the ground state of the system. SALMON solves the Kohn-Sham equation for electron orbitals based on the density functional theory. SALMON uses a uniform grid for 3D Cartesian coordinates to represent the orbital function of an electron. SALMON uses norm-conserving pseudopotentials to illustrate the interaction between electrons and nuclei. The Coulomb potential between the electron and nucleus diverges like 1/r at a small distance of r of the electron from the position of the nucleus. It is difficult to represent this rapidly varying potential with a 3D uniform grid. Calculations using pseudopotentials address only the valence electrons and not the electrons in the inner shells. By removing the electrons in the inner shell, the pseudopotential for valence electrons behaves smoothly even at the position of the nucleus. This figure depicts the norm-conserving pseudopotential of carbon atoms. The shape of this potential depends on the angular momentum of the electron with respect to the ion. The potential for zero angular momentum is a shallow potential at the position of the nucleus as a result of the removal of the inner shell electrons. Let us begin the calculation of the ground state. The files required for this calculation are contained in the salmon/samples/exercise 01 C2H2 GS/ directory. Let us copy the files to the directory where the calculations are to be performed. c2h2_gs.inp is an input file. c_rps.dat and h_rps.dat are files of pseudopotentials of the carbon atom and hydrogen atom respectively. Let us examine the contents of the input file c2h2_gs.inp. In SALMON, input files are described using the Fortran name list. All files that begin with exclamation symbol are comments and are therefore omitted. The first item in the name list is its name. This item begins with the ampersand symbol and ends with the slash symbol. In the first name list ampersand calculation, the item calculation enclosed in quotation marks is its name. Theory is the keyword, and its value is DFT. Multiple keywords in the name list may be written in an arbitrary order. For keywords whose default value is set, this value would be used if the keyword description is omitted. The keyword theory in the name list calculation specifies the type of calculation that would be performed. DFT specifies that the ground state calculations would be based on the density function theory. You can view the list of input keywords by clicking Theory on the website. All the options are written there. Sysname in the control name list specifies the name of the output file. The unit system in the name list units specifies the unit system of the files to be described in the input file. A_EV_FS indicates that the units angstroms, electron volts, and femtoseconds are used to represent length, energy, and time respectively. The default for unit system is the atomic unit system. YN_periodic in a system name list specifies the boundary conditions for the electron orbital function. Y implies that periodic boundary conditions are imposed. N implies that periodic boundary conditions are not imposed, that is, isolated boundary conditions are imposed. N equals 2 specifies that the acetylene molecule contains 2 elements. N equals 4 specifies that the acetylene molecule contains 4 atoms. N equals 10 specifies that the molecule has 10 valence electrons. N state equals 6 specifies that calculations are performed on 6 orbitals. Because an acetylene molecule consists of 2 carbon and 2 hydrogen atoms, it has a total of 14 electrons. Because the calculations use pseudopotentials, we do not calculate for the 2 electrons in the inner shell of each carbon atom. Therefore, there are 10 valence electrons. Because 2 electrons with opposing spins can occupy an electron orbital, the electrons occupy 5 orbitals. N state equals 6 implies that calculations are performed on an unoccupied orbital in addition to 5 occupied orbitals. The name list pseudo specifies keywords related to pseudopotentials. File_pseudo specifies the file name of the pseudopotential. Here we use C_RPS.dat and H_RPS.dat. Iz atom is the atomic number of the first and second elements. L-log_PS specifies which angular momentum potential is considered as the local potential among the pseudo-potentials that differ from each angular momentum. The keyword XC in the name list functional specifies the exchange correlation potential to be used. Here, Purdue and Zunger's local density approximation LDA is specified. The name list R-grid specifies keywords related to the spatial grid. DL123 is a 1D array with 3 components. It specifies the increment in the space length in the X, Y, and Z directions. If unit underscore system is A_EV_FS, the unit angstrom would be used. num_R_grid123 specifies the number of grids to be used in the X, Y, and Z directions. The product of DL and num_R_grid specifies the size of the rectangular parallel piped to be calculated. The name list SCF specifies self-consistent field iterations. NSCF specifies the maximum number of iterations. Threshold is a parameter used to access the convergence of the calculation result. The name list analysis specifies the type of output file to be generated. An orbital function would be generated when yn_out_psi is set to y. Other keywords also specify the output of the relevant file. Finally, $atomic_COOR specifies the position of atoms. Because the acetylene molecule has 4 atoms, the data is written in 4 rows. In the first row, C is the symbol of the atom, and the 3 numbers that follow specify the X, Y, and Z coordinates of the atom. The final number, which is either 1 or 2, specifies the element. Here too, unit_system equals A_EV_FS implies that the coordinates of the atoms are specified in units of angstrom. Refer the list of input keywords on the website for the name lists and keywords available in your input files. All the keywords are explained there. Let us perform the calculation. In the system used here, the command for Mpi calculation is mpi exec. Here, calculations are performed with the Mpi process count as 2. When the calculation is completed, several output files would be generated. A sample output file can be downloaded from the SALMON website. Let us observe the contents of a few of these files. First, let us consider the standard output file c2h2_gs.log. The first part of the file shows the version number of SALMON used in the calculation. Then, the input variables used in the calculation are displayed. When the preparation for calculations is completed, the SCF loop would begin. The SCF loop number is shown by ITER. Then the total energy and the energy of the 6 orbitals are shown. The SCF iteration has converged after 163 iterations. We can observe that the energy has varied negligibly compared with the preceding 162 iterations. When the SCF iterations are completed, information such as the force acting on the atom and the orbital energy is displayed. Let us briefly consider the other output files. The directory data_for_restart contains data such as the orbital function in the ground state, which form the input file for the time evolution calculation to be performed in the next step. C2H2_info.data contains data such as input variables and total energy. C2H2_eigen.data contains data on the orbital energy. Psi_ob1.cube, etc. is a cube file for drawing the spatial distribution of orbitals. DNS.cube is a cube file for drawing the spatial distribution of electron density. DOS.data is the data on density of states of electrons. ELF.cube is a cube file for drawing the spatial distribution of electron localization functions. It is feasible to develop an image of the ground state of the acetylene molecule by using the cube files. The first is the homo-orbital distribution of electrons. The second is the distribution of electron density. The third one is called the electron localization function. This concludes the explanation for exercise 1.